X21, what is a wave? A wave is a distribution of fluctuation of many particles called medium from the equilibrium state in space. Yes, it's right. The wave function of a wave describes the space-time fluctuation of the wave. Sure, the propagation of a wave can be inferred from the change of the wave function depending on t prime that is greater than t and x. And the wave equation shows the propagation of wave. The medium of a wave consists of elementary particles that are not continuous but quantized in nature. Sure, all of the elements in a macroscopic scale, we can assume it can be a continuous distribution. However, in fact, they are all consist of quantized particles. So we should be careful about that. Any mechanical wave requires corresponding medium. Unlike mechanical wave, light waves do not require any medium. Yes, that's correct. So light wave travels in a vacuum. However, sound wave cannot propagate in vacuum. So this is a wave. Okay, there are two waves, psi1 and psi2. Red one is propagating from the left to the right, and blue one propagates from the right to the left. And the amplitude of the two waves are the same. And actually, we call this kind of wave as a pulse. This is not a sinusoidal function that is wavy all over the space, but we have a wave at a certain region, and except for a specific region, there is no fluctuation. It is called pulse. And two pulses collide, and as time develops, they have some overlap, and gray curve shows the resultant wave of the two waves. That means it is an algebraic sum. Psi1 plus psi2 is the resultant wave. And at t equals exactly 0, the two waves overlap. That means it is exactly twice of each wave at this point. As time goes on further to the positive sense, the relative positions of the two pulses are reversed, and they are finally separated. This figure demonstrates the propagation of two waves, and in the middle of their propagation, they meet together to have a very strong interference. After that, we find that the two waves are actually traveling independently. This is the big difference between the wave and particle. If the two particles collide, then if they do not miss, then they will bounce back. 1, 2. They won't exchange the position. However, the two waves, each of the wave is transparent to the other. That means the propagation of a red wave is not interfered by the blue wave, and vice versa. So the red wave does not bounce back, it just travels forward with the same velocity, like that. And that is true for the blue wave too. So particle nature and wave nature are absolutely different. These are the explanation of what I have already told you. So we would like to construct a physics model of such kind of waves. We can describe a wave in terms of motion of a system of weakly bounded and simple harmonic oscillators. For example, we have an oscillator, spring constant and mass m, and frequency is square root to k over m. It oscillates. If I put this oscillator here and another oscillator, they were at rest, and let it oscillate, left one. Then as t goes to t develops, only this one is oscillating. However, what happens if I connect the two masses with a very weakly interacting thread, just like it's a very thin but flexible thread with the constant kappa, spring constant kappa, that is much less than the spring constant of these springs. Then, if we carry out an experiment, then this oscillation, this motion is transferred to the right oscillator, and as time goes by, this one, left one, stops suddenly, and then this guy oscillates. And this oscillation goes back and forth. This is a trivial, the fundamental wave nature based on the weakly bounded two-body system. And what happens if I connect many, many masses with a spring? And I move this one a little bit and let it release this. Then this one oscillates, and as time goes by, this oscillation propagates to the neighbors. And if you look at the global picture, you will see the wave propagation. So this is a kind of a physics model of waves. By making use of system of harmonic oscillators that are connected with a weak spring. So this one stands for the weakly bounded and simple harmonic oscillators. The phase difference of different points determines the shape of a wave. Yes, if this spring oscillates and another spring oscillates, and there is some time delay, then you will see the mass distribution. There is a spring, something like that. They oscillate. Actually, each of them oscillates up and down, and you can see the phase difference of nearest neighbors. This phase difference will give the shape of wave. If we consider a system of n particles, we need 3n Cartesian coordinates because each particle has 3 coordinates. Okay? We have a function of a one-dimensional wave that can be described by the coordinate of the ith point mass on a string. Okay. We have a long string and distribute B's on the string and coordinate x1, x2, x3, something like that. Coordinate x that represent the deviation. For example, identify a 1, 2, 3, and n particles, and we allocate coordinate x1 that is the deviation from this is the equilibrium point of each oscillator, and it has been deviated from the equilibrium position. Let me call this one x1, and that x2, and so on, x3. Then it gives a shape x5, x6, and so on. So distribution of this sequence, if we draw a plot, this sequence gives a shape of a wave. Okay. The continuum limit, this is the discrete model. N particle. So this is integer. We say it is a discrete model. And if we increase the number of particles attached to the string, then it becomes a kind of rope. And we say, we take the limit n goes to infinity, and tiny mass, let it go to 0. However, keep the number of particles multiplied by each particle's tiny mass to be the total mass of the string. Then we say this kind of limit is a continuum limit. So using this discrete system and take the limit of a continuum limit, we would like to construct a theory of a wave. There are various waves, but mostly they are classified into 2 pieces. This red arrow shows the velocity of a propagation of wave with respect to the direction of propagation that is parallel to the wave vector of each wave. The fluctuation of each particle placed at every point of propagation, the deviation from the equilibrium point is perpendicular to the direction of propagation. Then we say it is a transverse wave. Transverse means it is perpendicular to the direction of propagation. There is another wave, and actually this transverse wave is a wave in the sea, wave in you can see the wave of a flag. This is a transverse wave. It is propagation and the fluctuation, they are making right angle. And electromagnetic wave, electric field, and magnetic field are always perpendicular to the direction of propagation. There is another wave whose fluctuation is along the longitudinal direction. Longitudinal means the direction of propagation. So the particles are densely distributed in this region. It is less dense, less dense, dense. So there is a periodicity in space. This kind of wave can be found in the sound wave. Okay? If each oscillator in medium, this bar represents each oscillator in the medium vibrates along the direction parallel to the propagation, this longitudinal vibrates along the direction perpendicular to the propagation, this transverse. The wave of a violin string is dominantly a transverse wave. Yes, violin string vibrates perpendicular to the direction of propagation. Sure, because it is elastic, the mass can oscillate longitudinally, but dominantly the motion is up and down. That is perpendicular to the direction of propagation. The sound wave is a typical example of a longitudinal wave. Yes. Mechanical wave, water waves, sound wave, seismic waves underground, right, are examples of mechanical waves. Okay. Newton's laws of motion extended to a system of many harmonic oscillators can explain the physical phenomena involving the mechanical wave. Yes, that's what we are doing in this today's class. Mechanical waves can travel only through a medium. Yes. However, the electromagnetic wave, including light wave, can travel without medium. Sound wave cannot propagate in a vacuum. Sure, while it travels in the air, water, and solids. Any visible light travels with the speed of light 299,792,458 meters per second exactly in a vacuum. In a medium, it goes down. The speed of light in a medium is defined by C over N, and for any matter, N is greater than 1, and N is 1 only for the vacuum. Ultraviolet and infrared lights are all electromagnetic waves. X-rays a wave, the electromagnetic wave, a radio wave, anything can propagate with the speed of light in vacuum. A light wave can travel through a medium, sure, but it slows down. Microwaves, that is also electromagnetic wave, television waves, radar waves. Without electromagnetic waves, you cannot communicate with your cell phone. Matter wave, sure, there is a new kind of wave that is a matter wave. Any elementary particle shows the nature of the matter wave, and we will learn in the next semester in this Physics 2, General Physics 2, atoms and molecules show the nature of matter wave, so they must be described not based on Newtonian mechanics, but based on the quantum mechanics, that respects the wave nature of matter. An electron behaves like a light wave in the sense that the probability of finding a particle in space is related to the wave function. Yes. Quantum mechanical features of elementary particles show that they satisfy the wave nature. Yes, we will learn in detail in next semester. This is a very simple definition of wave. We have a very strange distribution of fluctuation, and the shape is invariant. In that case, it is described by a simple function. At t equals 0, this distribution is described by a single function of a position at t equals t0, as shown in here. And as time goes by, from t0 to t, if it translates with the same velocity v, then the position of each point has been translated from here to there. The distance of travel is delta x, that is velocity, multiplied by the time difference, t minus t0. A middle school student can draw a figure of a function of f of x, and if the function has been translated by plus a, then the equation of the curve y equals f of x is translated to f of x minus a. When we translate this function by plus a, then we substitute x minus a for this with x. The distribution, the fluctuation of this wave is perpendicular to the direction of propagation. So this wave is transverse. Propagation velocity is v. Yes, right. Shape of wave is invariant as time goes by. Same shape. And we have a translation. So this function is exactly transformed to this function. What we have done is by subtracting v t minus t0 to consider the translational operation. All right. Because v is a constant vector, the partial derivative with respect to x and partial time derivative of this function, they are closely related. And in the main text of X21, I have derived the equation of motion from this relation. This equation of motion shows 1 over speed of propagation, velocity squared, double time derivative subtracted by Laplacian. And Laplacian is this one. And that is second order derivative of x, y, and z sum. Okay. These are the waves, and I have listed the way to determine the direction of propagation. Now, we have a bottle. There are masses, identical masses, distributed with equal spacing d. The length of this string is L. We have n bees, so the space is 1, 2, n. So this is d, this is d, so the whole length is n plus 1 d. Mass is n bees with the small m, so this is total mass. Density of this string is the total mass divided by length, and in the limit, as n goes to infinity, the density of this string is small m over d. We have a finite value for this density, length, linear mass density of the string. Longitudinal position. Longitudinal means the propagation direction of the wave. We allocate integer. This is the integral multiple of d, that is common spacing. And this d is actually the difference between the nearest neighbor, so I can make use of delta x. If I sum the difference between the two nearest neighbor from 0 to n, here r is 0 and 1 to n, and r equals n plus 1. And these two words are fixed. Using similar method, I can do this summation. However, the good point to take the continuum limit allow us to evaluate the summation in terms of integrals. Integrals are more convenient to evaluate. Using this way, I can describe the velocity of each particle. This each particle's fluctuation is identified by the psi r, where r runs from 1 to n, and this is n plus 1 and 0 are fixed. If I keep r and change time, I can evaluate the velocity, vertical velocity. This is a transverse wave, vertical velocity of each b by taking the partial time derivative of wave function. So this is a sequence, and this sequence distributed over the space is to be replaced with a wave function psi that is a function of position. This is continuum limit, discrete model. And if I want to compute the acceleration to evaluate the force, then I would make a double time derivative. And this double time derivative will, and multiplied by the mass of each particle, I can obtain the force, the Newton's law of force. And there is one thing missing. We have tension tau. Tension tau. There is a tension. String have a tension. This is the force applied to each particle, each rth particle. There is r plus 1 and r minus 1. And tension is not compression force. It is a tensile force. So this these two forces are to be applied to this particle. And actually, if the angle theta at each point toward the nearest neighbor is small enough, then I can say the string has a tension tau, and at each point, the force applied to this bead, earth bead, is nothing but tension multiplied by sine theta, because cosine theta is along this direction. These two longitudinal forces cancel almost exactly, and only the transverse force applies. And on the right side, if the angle is a positive, it is upward, and the left side, if the angle is like that, it is negative. So we have plus minus value. Therefore, the angle can also be evaluated by making use of the difference of the coordinate, psi r and psi plus r plus 1, and psi r and psi r minus 1. So using this method, I can evaluate this angle, and that is difference of the position, and this is the width d. This is a spacing of two beads. So if I substitute this one to the equation of motion, what I really find is that the sum of two forces applied to the earth bead, difference with different indices and their difference. And actually, this one, they are the limiting value as d goes to 0 is the first order spatial derivative with respect to x. And the first order derivative's difference is actually the second order derivative with respect to x multiplied by the width d between the width between the spacing between the two nearest neighbors. If I substitute this one to the equation of motion one that we have obtained, finally what we obtain is the wave equation, and this wave equation determines the what determines the speed of the wave propagation. So from this, we can determine the wave propagation speed in a string of linear mass density rho and tension tau is exactly square root tau over rho. Let me tell you the final result for this kind of wave, and the solution for this equation of motion that is identical to what we have written in here. Solution can be found by substituting a trial solution, and at the end of the day, what we can obtain is the specific frequency, and this frequency shows there are 1 to n frequencies. These n frequencies represent this number of frequencies, available frequency, that are quantized, first quantized, and the number of frequency is identical to the number of oscillators. We had n independent oscillators. However, that n independent oscillators are combined to make a system of oscillators to generate a wave. That wave has n distinct frequency. That's a very important. And in addition, if I take the limit, n goes, s can vary to 1 to n. If I substitute this n here and take the limit n goes to infinity, then we have the value sine half of pi, that is 1. That means there is a maximum value of a frequency. That is the maximum value of the frequency. That actually we can find that the string vibration has the wavelength that is half of wavelength. This is the half of a wavelength. And then we increase the, from this we can increase the frequency. And this increasing frequency we learned from the elementary school is this is a basis to construct an instrument, musical instrument. And the basic theory comes from Pythagoras, and Pythagoras derivation is completely wrong in the limit and goes to infinity. Pythagoras' formula that the fundamental harmonic and dividing this one by the integers is true only for a very small s. In that region, sine of x can be approximated with x. In that case, it's right. The frequency is a linear, the integral multiple of a fundamental frequency. Okay, this is the very basic nature of a wave described in terms of n harmonic oscillators. And this is very important to understand the quantum nature. Even though it is a classical mechanics, this method is a very, very important to understand the quantized nature of quantum mechanical system.